Thank you for the kind invitation and also for the kind introduction. My name is Marco Bonhoff. I am a professor for borehole seismology. I'm currently head of the GFZ section, Geomechanics and Rheology. That is one of approximately 20 sections at the German Research Center for Geoscience in Potsdam. Geo-research in Potsdam has a long history. As you have heard this morning, it was the place where the first teleseismic earthquake was recorded by chance in 1889. And what I'm going to present you today is an overview of ongoing research that we are conducting in the broader Istanbul-Marmara region. This morning, you have already heard excellent introductions in the broader Mediterranean region from a tectonic point of view. You've also heard something in general on earthquakes. And in my talk, I'm trying to combine both, giving you a sort of background on the earthquake processes that we're trying to understand. And also, I'll at the same time focus on the application with regard to seismic hazard for the Istanbul metropolitan region. So before I focus on the broader Marmara region, I'll give you a very short glimpse of what our main research aim is, which is trying, on the long term, trying to understand the physical processes which start and also stop earthquakes. And this, of course, is a very broad research topic. I try to give you a very short overview on what is behind the term earthquake, and I'll then focus on two main points. The first one will be what we know and don't know about the overdue Marmara earthquake and its maximum earthquake magnitude. It's very important to estimate maximum magnitudes of pending earthquakes because basically the magnitude defines the seismic hazard and associated risk. And then in the second part, I'll give you an overview of our current research activities, which is basically a plate boundary observatory which we have installed in that region to monitor as much as possible of the small earthquakes. And we're using these small earthquakes to better understand the physics and the processes of the pending big one. Yeah, let's start with a very general picture. This is the Richter scale. You have heard about earthquake magnitudes this morning. This is a logarithmic scale. And it's quite easy to draw that scale here, a few numbers or so, but it summarizes or covers a broad range of rupture processes. And if we start at the smaller end of the Richter scale and just focus on magnitudes as small as -2 or -1, those earthquakes can be represented by this nice table here. An earthquake is not a point, as you probably see it in the news every day or every other day, but an earthquake always is a shear failure of two planar surfaces. And these planar surfaces, they move against each other. And in case of a magnitude -1 or -2 earthquake, the surface that moves is on the order of this table, so about a square meter or so. And the two planes that are moving, or the two surfaces that move, they move on the order of a few millimeters. And based on these two numbers and then another constant, you can quite easily calculate the seismic moment and then the earthquake magnitude. So if we look at the other end, at the upper end of the Richter scale, talking about magnitude 7 or larger, the process is exactly the same, two surfaces sliding against each other, but the surfaces are much larger. And this is a reconstruction of the Sumatra earthquake of 2004, which happened offshore Sumatra and caused the tremendous and big disastrous tsunami. In that case, the two surfaces that moved against each other were on the order of thousands of kilometers. So approximately 1,000 kilometers long, 50 kilometers deep, and these surfaces, they moved by about, on average, let's say 5 meters or so. So this, of course, has dramatic implications, but the process is the same. And that is important, especially when it comes to aiming at understanding the governing processes. And so the main philosophy of my working group at GFZ in Potsdam is to investigate these processes over the entire scale, extending from tiny little rock samples that we deform in the laboratory, in our rock deformation lab, where we produce, so we squeeze these until they fail and they rupture. And the advantage is that if we do this in the lab, we can have a look at the rupture surface afterwards. So we have the rock specimen that failed, we can open it up and look at the earthquake process. And during the deformation, we're creating thousands of laboratory earthquakes, which are called acoustic emissions. And these can be investigated using the same methods that we use to investigate natural earthquakes. So with laboratory earthquakes, we're typically on the order of magnitudes way below -2, down to -8 or so. And in that case, then the rupture surface is just about a square millimeter. Now, going one step further to a larger spatial scale, we have earthquakes also in geo-reservoirs. These are earthquakes which are usually called induced earthquakes, which you may know from wastewater disposal or from fracking or geothermal projects. This has been quite prominent in the media about during the last decade from induced seismicity in the central US. At the end, these are the same physical processes, again, two small surfaces rupturing against each other. And these are magnitudes about from -2 up to 3 or 4 or so. And the third spatial subdivision of these rupture processes are natural earthquakes, and that's what I'm going to focus on in the next 30 or so minutes. And here we're talking about magnitudes 0 or larger, extending all the way up to 7 or 8. You have also heard this morning that the largest ever recorded earthquakes had a magnitude of 9.5. That is also the largest earthquake magnitude that physically makes sense because it's a logarithmic scale. If you would talk about a magnitude 10 earthquake, that would mean that we have one San Andreas fault all around the Earth being activated at once. Magnitude 11 would mean that the whole Earth would break in two. So that's physically possible, but not reasonable at all. So 9.5, which was the magnitude of the Valdivia or the earthquake in 1960 offshore Chile, is probably the largest earthquake that we can measure at all, or that can happen at all. So in the case of Istanbul, and that's what I'm going to focus on in the following, the maximum magnitude is on the order between 7 and 8, and I will go into more detail here throughout my talk. Good. So let me start with a brief introduction into the tectonic setting of that region. You're already well informed about the tectonics of the entire Mediterranean Sea. So in the Aegean Anatolian region, with basically two major deforming plates. We have the Anatolian plate that moves with about 2 centimeters per year with respect to Eurasia. Eurasia is always the framework. So these arrows here are measurements from GPS stations, and they tell you about the velocity in centimeter per year. 2 centimeters per year is approximately the velocity that your nails grow. And if you have this kind of movement over millions of years, you have displacements on the order of tens of kilometers. So the Anatolian plate is rotating in a counterclockwise direction. And this plate is rotating because there is a push from the Arabian plate. So the Arabian plate moves to the north. And then there is a pull from the Aegean plate, which moves to the south. And if you have a northward push in the east and a southward pull in the west, the result is a counterclockwise rotation, which you see quite nicely by the arrows here. So since this plate is moving with respect to Eurasia, there has been a plate boundary that evolved, and that is indicated by the red line here. That is the so-called North Anatolian fault zone, and it's a transform fault boundary where two plates move against each other, and this fault zone is producing large earthquakes. And what you see here, this big black dot, is Istanbul, with today on the order of 13 to 15 million inhabitants. And unfortunately, this metropolitan region is located in direct vicinity to the thick red line here. And to tell you, or to show you how close the city is actually located to the fault zone, this is one very small piece of the city of Istanbul, which is also including the historical city center. So this is Hagia Sophia here, the Blue Mosque. So this is the Bosporus. These dots here are the Princess Islands, which I show you later in more detail. And the fault zone, which will produce an earthquake in some near future, is running exactly here. So that's just 15 to 20 kilometers away from the historic city center. And a large earthquake in that close vicinity to a metropolitan region with this kind of building structure obviously produces a lot of seismic risk. So back to the tectonic setting. Over the last century, we have seen a remarkable sequence of large earthquakes along this fault zone. And this started back in 1912 with a magnitude 7.3 earthquake here, and then continued in the east in 39, systematically progressing towards the west. And these are all earthquakes larger than magnitude 7. 99, these were two earthquakes, which are until today the two most recent ones. And the only part of the entire fault zone that has not produced a large earthquake since 1766 is this red line here. So it's not a question if there will be a large earthquake, it's just a question when will there be a large earthquake, how big will the earthquake be, and what would be the rupture propagation. That's what I'm going to talk a bit in more detail. That's pretty sophisticated, but that's important because the rupture propagation directly also defines the seismic hazard and risk for the city. So to sum up, first of all, this kind of seismic cycle is unique. It's not observed at any other fault portion in the world. And there are some indications that such a systematic seismic sequence has also occurred in the past, like 1,500 years ago and 2,000 years ago. But of course, the further you go back in time, the less well constrained are the data based on which you can develop your model. And so if we sum up what we know as boundary conditions, we know that there have been several earthquakes larger than magnitude 7 in the broader Istanbul region. The average recurrence period is on the order of 200 to 250 years. And since we know that the last main earthquake was in 1766, if you add 250 years, you're in 2016. So if that recurrence period would be constant, it's just about time. But the recurrence period is not constant. So there's not one earthquake every 250 years. There's one earthquake every 250 years on average. It might be 100 years, it might be 300 years. We don't know that. So currently, there is a high probability. This is usually how we calculate the probability for large earthquakes. For the Istanbul region, it's 35 to 70% for an earthquake larger than magnitude 7 in the next 30 years. And this estimation is already more than 10 years old. So by now, the probability has increased. Now, one important question is whether a fault in general, and especially this red part of the North Anatolian fault zone here, whether it is creeping or locked. We know of such faults that creep, which means there's no stress buildup, but we also know of faults who are completely locked, so who are blocked, and then in that case, there is a stress accumulation, which is then released in one large earthquake. And again, I want to focus on this in more detail later in the talk. Yeah, so there are documented tsunamis for this region. These are not tsunamis on the order of what you know about the Japan or Sumatra tsunamis. These are local tsunamis, but in historic times, these local tsunamis have reached waves of 6 meters or so, which produces some hazard for the coastal area. But the tsunami implications most likely would not be even close as large as in the two large earthquakes I've mentioned, Sumatra and Japan. Now, the population in Istanbul has increased dramatically over the last 65 years, from about 1 million in 1950 to 13, 14, 15 million these days. And the most important factor defining the seismic risk is, of course, the building structure. As of today, the building structure, or the building code, not the building structure, the building code in the region is similar to the building code in California or Japan, but the problem is that probably 80–90% of the buildings do not fulfill these codes. And that's what creates the large risk in this region. And of course, there are also huge socio-economic implications in that the Marmara region generates approximately 40% of the Turkish GNP. So these are just some facts and figures. And in the following, I'll focus more on what we do or what other colleagues have been doing in the recent years to better estimate the hazard and to provide the engineers with numbers to optimize the building structure. Now, what I've mentioned before that the crucial number that defines a seismic hazard is the maximum expected earthquake magnitude. And to know or to estimate this number, you need a good historical earthquake catalogue based on which you can estimate that magnitude. In that respect, the North Anatolian fault zone is a very fortunate region because there we have a long settlement history with good historical documentations which allowed us to estimate or to compile a historical earthquakes catalogue, which I'm going to show you in a minute. This situation is completely different, for example, at the San Andreas Fault in California, where we have basically no such data for times preceding 500 years ago. So that makes it very difficult for large portions in California to estimate the maximum expected magnitude. Second, it's still difficult to estimate the maximum magnitude because the big earthquakes, they don't occur every year, but as I mentioned, they occur only every 200 or 250 years. But we only have good instrumentation since approximately 100, 120 years. So that means with modern instrumentation, we have not even catched one of the big earthquakes in the Marmara region. And that is why we need to rely on historical data. So, and this is one study which I would like to briefly summarize. Historical earthquakes along the North Anatolian fault zone are very well known due to the good historical record. We have two events that are as big as magnitude 8. First, there's the Erzincan event, which happened in 1939. That happened in the eastern part of the fault zone, so far away from the Istanbul region. There is a second very large earthquake, the earthquake of 1668, that also probably had a magnitude of 7.9. Of course, there's a certain error attached to these numbers. So the larger the earthquake, the smaller the error bar. In this case, probably we can state that the magnitude is 7.9 plus minus 0.1 or 0.2. So, and so this earthquake, let me show, that is actually that one here, 1668. So that was, these two guys are the two largest earthquakes. And then for the Istanbul region, because of the long settlement history, we have quite a detailed picture. We have a number of earthquakes where we can reliably estimate the magnitude, dating back to almost 2,000 years ago, magnitude 7, 7.1, 7, 7.2, and so on. And what you see between these two parts here, there have been magnitudes up to 8 in the eastern and central part of the fault zone. But in the Istanbul region, the largest magnitude is 7.4. Now you can say 7.4 and 8, that's not much of a difference. It actually is. Because it's a logarithmic scale, it's a big difference if there would be a 7.4 earthquake or a magnitude 8 earthquake. And so we investigated this further, and I won't go into detail here. So we collected all available information on historical earthquakes. We unified the magnitude. In seismology, you have different magnitude scales, surface magnitude, body wave magnitude, and so on. I don't want to go into too much detail here, but we unified this in order to be able to compare the magnitudes of the historic earthquakes. And at the end, we came up with a catalogue of historical earthquakes along the entire fault zone for the last 2,300 years. And this time period is very important since the longest recurrence period so the longest time interval between two large earthquakes at one location is 685 years. That means for every part of the whole fault zone, we have at least 3 seismic cycles. That means the catalogue has some sort of reliability. So, and the new earthquake catalogue now contains 203 earthquakes, and this catalogue is complete down to magnitude 7.3. That means we don't know anything about the many small earthquakes, but we did not miss any earthquake in the catalogue that is larger than 7.3. Okay, and that's how the catalogue looks like. Since the fault zone, as you may remember, runs basically from west to east, we have plotted the maximum earthquake magnitudes here from west to east. And these are the numbers. So on the vertical axis, you have the magnitudes. The vertical red bar here is the arrow for the magnitude. And the horizontal bar here is the rupture length along the fault zone. And what you see is, what I mentioned before, that in the eastern part, you have earthquakes as large as approximately magnitude 8, while in the western part, which is including the region of Istanbul, there has been not a single earthquake with a magnitude larger than 7.4, and if you add the arrow, it's 7.5. And this is fundamental information to give an upper boundary of the earthquake magnitude that we would expect for the region. So we can probably exclude that the next earthquake in the region would have a magnitude of larger than 7.5. And this, of course, is an important constraint for the building code and so on. So to focus a bit more on these findings in the seismological or a scientific sense, so you remember that the largest earthquakes occurred here in the east. In the west, still, we do have large earthquakes, but not as large as in the east. And if we put together additional information that we have, which is, for example, the age of the fault zone, then we see that the fault zone is 12 to 13 million years old in the eastern part, while it is younger, only 8 million years old in the western part. So basically, the fault zone, well, the fault zone does not fall from the sky, it evolves. And in this case, it shows a quite systematic evolution in that 12 or 30 million years ago, the fault zone started to evolve, it developed further to the west, and it reached this region not earlier than 8 million years ago. And then it continues further to the west where it's still younger. And if we correlate this, we can come up with the conclusion that the maximum earthquake magnitudes scale with fault zone age and length of coherent fault segments, but this I don't focus on right now. So the older the fault zone is, the larger the earthquake. And that is something that we actually know from laboratory experiments. If we take a rock sample of this size and if we start to deform an intact piece of rock, we have tiny little cracks here and there. And if we further deform the rock specimen, then these tiny little ruptures will coalesce and form larger ruptures, larger earthquakes, and at the end the whole specimen fails and produces a large earthquake. And that's the same what we observe on a field scale here. So when a fault zone evolves, when it's young, it produces small earthquakes, in this case up to magnitude 7.4, but not larger, while here we have large coherent surfaces. Okay. So with this, I'd like to move on to current research activities in that region. We know that the earthquake that is expected for the near future in this region will probably not be larger than 7.4. But we also would like to understand in more detail the local seismic hazard. And I will try to explain you why we need to know more and then explain what we're actually doing to better understand what's going on. So the colored lines here are individual parts of the North Anatolian fault zone. And all the segments which are in orange and red here, they have already produced a large earthquake. In this case, the most recent Izmit earthquake in 1999 and then the Düzce earthquake. So here we already had an earthquake 17 years ago. In the west, along the Ganos segment here, we also already had a large earthquake, which is already more than 100 years ago. But the region that has not produced a large earthquake is represented by these lines here below the Sea of Marmara. And these three segments, 1, 2, 3, and you may add this one, if they would be activated in one large earthquake, it would mean that we have an earthquake magnitude of 7.4. Okay, but it's very important whether this earthquake would start from this point and then rupture towards the west, or whether the earthquake would start to rupture here and then move towards the east. An earthquake, again, is not a point, it's a surface, and in case of such a large earthquake, the whole surface is not activated at once within a second or so, but it takes a minute or 20 seconds or something. It takes something on the order of tens of seconds for this earthquake. So such an earthquake nucleates at a certain point, and then the rupture propagation is along the main fault. So if the earthquake would start here, it would mean that the rupture propagation would be towards the west, which would mean that the ground motion, and the ground motion defines the hazard and the risk, is larger in the west than in the Istanbul region. That would be the good news. The bad news would be that if that earthquake would nucleate here, the early warning time is a minimum. So the early warning time is the time between the first recorded P waves, when you define there has been an earthquake, and the time where the S or surface waves, so the later waves that produce more energy, arrive at a certain point. So if that earthquake would nucleate here, it would mean a warning time of only 2 to 6 seconds, which is virtually nothing. If you have a fully operational early warning system, a few seconds are unfortunately not enough to warn people, to allow people evacuating from houses and so on. It's probably just enough to close gas pipes, to put traffic lights on red, to close bridges or so. So if that earthquake would nucleate here, there would be a short warning time, while the ground motion would probably smaller than in the opposite case. And the opposite end member now would be that the earthquake would nucleate here. Then we would have a rupture propagation towards the city, which would result in larger ground motion. That's, if you want, is the bad news. And the good news is that the warning time would be longer, but still only on the order of 10 seconds. So that's not good anyway, but that's defined by the geometry between the fault zone and the population center. Now, the main aim for our research is to characterize these lines here as best as possible, based on as many as possible small earthquakes. You may have heard in the morning, I'm not sure, but let me briefly mention this. The smaller an earthquake, the more the earthquakes are in number. So at the time when there is one earthquake of a magnitude 4, at the same time there are 10 earthquakes of magnitude 3, 100 earthquakes of magnitude 2, 1,000 earthquakes of magnitude 1, and so on. So the smaller you can detect, or the lower you can generate your detection threshold of a seismic network, the more earthquakes you can record, and the better you can characterize a fault section. And that is what we're basically aiming at with the ongoing research. So we're looking now in more detail on the setting again. So the red line here is the Princess Island segment, or the Marmara section of the North Anatolian fault zone that runs undersea. That is the line that is probably expected to generate the next major earthquake. There's a second branch here that is also known to generate, in part, large earthquakes, but the main focus would be on this line, since it is closer to Istanbul, which is located up here. The black line is the fault that has already been activated back in 1999. And we don't know exactly where this earthquake had ended. We know it is somewhere below the eastern part of the Sea of Marmara. And there are some seafloor observations which give some indication on where the rupture stopped, but we don't know in great detail. But it would be somewhere here. So the next earthquake then would probably activate this segment then and further to the west. Now, based on the existing permanent Turkish seismic network, which is indicated by these blue and yellow squares here, based on this network, magnitudes down to 2.8 can be monitored. So that means that every earthquake larger than 2.8 can be detected and can be located, but the smaller ones cannot. And that was motivation for us to improve this situation. And the way we did this is we selected the Princess Islands group here, which is located between Istanbul and the fault zone. And this was an opportunity to install seismic stations on these islands, because that allowed us to go closer to the fault, and going closer to the fault means we can also detect more smaller earthquakes. And in part, so these are the larger islands here. We have installed individual stations on the larger islands. And in part, there are also two very small islands with a diameter of 300 meters. These are the two islands of Zivriyada and Yassiada. And on these islands, we have installed local arrays, so in higher station density, in order to improve the detection threshold. And well, seismology is a great job. It's nice to sit on the desk and work on data. But to get the data, you need to install stations, and that in part can also be a tough job. So in this case, as I've shown you, every circle here is an individual station. And since these islands are pretty remote, transport is an issue and so on. And actually also vandalism was an issue. So at the beginning we had installed seismic stations at the surface, but then we were confronted with the fact that cables were stolen, solar panels were stolen and so on. And that led us to conclude that we actually really built bunkers with concrete with wall thickness of 10 or 15 centimeters or so, which then allowed us to protect the stations. And by now, the only problem that we're having is that there are actually people going on a boat with a gun shooting at solar panels. And so every other time or so, we have to replace them. But otherwise, the stations are in good shape. So these are some impressions from the fieldwork. This is one of these small little islands, the island of Yassiada, which is located here. That actually has been a former prison in the until the 1950s and 60s. And this was how the island looked like when we started to build up our network back in 2006. By now, the whole island is reconstructed and remodeled. They are currently building a hotel fairly close to the fault. They're building a harbor here and so on, and we hope that we will be able and we'll get permission to maintain our seismic stations, because since this island is so close to the fault, it's very important since it generates very valuable data. And that's a Google image of this island. So all these red dots here are the stations. We have installed the stations in a cross-like feature which allows us to apply certain techniques, which are called array techniques, which allows to improve the resolution in getting as exact locations for earthquakes as possible. And that's then how such a station looks like. So that's basically the core of the station. Inside, we have the data logger, which is basically on computer. We have the seismometer. And then we have the steel lid and the concrete lid to close this. And of course, the solar panel has to stay outside, and also the GPS antenna. And these data are then transferred in real time to Istanbul, to mainland, and are basically available in real time for processing. So we made all this effort, and at the end, with the data we got, we can conclude that it was worth to make this effort. What you see here is a list of, or a map of small earthquakes which were recorded during the first 3.5 years. So we installed this network in 2006, and this is data from the first couple of years. These are about 800 earthquakes, and most of these earthquakes remained undetected before. So these are mostly small earthquakes that were not detected by the regional network. And so these allowed us to perform research. And in particular, for example, there was one earthquake swarm An earthquake swarm is a burst of earthquakes that occur within a short time. So while we have, on average, I guess, 2 or 3 events per week, we had more than 100 earthquakes per day, which is shown here. So this is the cumulative number of events. So within less than 21 hours, we had like 100 earthquakes. So we analyzed this in detail, and I don't want to focus on this in too much detail here, but this is basically why we're making this effort and install local stations. More importantly, based on these small earthquakes, we could come to a very important conclusions on whether this fault offshore Istanbul is currently creeping or whether it's locked. If a fault is creeping, the seismic hazard is very low, because if the fault is creeping continuously, it doesn't accumulate large amounts of energy. But if a fault zone is locked, the energy is accumulated and then released in individual large earthquakes. And based on our findings, and I will just briefly summarize this, we identified what we call a seismicity gap. So we have an area where no earthquakes occur. This is so that is the transect along the fault, and if you look with depth, then you see an area where no seismicity occurs, which we call an aseismic patch. And if we conduct further research, again, I can't go into too much detail here, we can conclude that this part of the fault is currently locked. And if it's locked, and if it looks like this, it also has to be considered as one potential nucleation patch of the incoming earthquake. So if the Marmara earthquake would nucleate in this region, it would be probably nucleating somewhere along this patch and then run westwards. And this, of course, has the implications that I mentioned before. There's further evidence for this, so also GPS data, although it's limited in this region, come to the same conclusion that this part just offshore Istanbul is currently locked. And remember that we're only like 15 to 20 kilometers away from the historic city center. Okay, so that findings were all based on the network that I've shown you. We had installed a couple of stations on the islands, but that's not the end of the story. We further intended to decrease the detection threshold to even detect more smaller earthquakes. And to do so, we have installed a borehole-based observatory. Why have we done this? If we record at the surface, whether it's in Istanbul, on the islands, on the southern shore, we always have a certain background noise level, which is created by wind, which is created by waves, which is created by city noise. And the only way to get rid of this noise, to have better monitoring conditions, is to go downwards, to drill boreholes and put the sensors down in the boreholes. But this is quite a costly undertaking. Drilling is very expensive, so this needs extensive planning and fundraising and so on. But at the end, we finally succeeded with this. And so let me show you this. So all these bold red dots here are boreholes which we have drilled over the last couple of years. And at each of these boreholes, we have installed a vertical chain of borehole sensors, so a couple of sensors at the surface, and then every 75 meters, different kinds of sensors. And then at the deepest part of the borehole, which is always 300 meters, we have installed an entire set of sensors, which allows us now to record small-scale seismicity under low noise condition, giving us a factor of 100 more earthquakes compared to what we can see from the surface. And so to conclude my talk, let me show you some of the results. This is how the borehole instruments look before deployment. So all these are tiny little earthquakes that we record down in the boreholes, in this case at the borehole in the southeastern part of Istanbul, where we observed another seismicity cluster here containing 100 events. And yeah, so this is basically one seismicity cluster. We can conduct further studies, and let me finish with showing you one remarkable example. The seismicity in this region in general is very low, which means there are not many earthquakes large enough to be located by the networks. Last year in summer, just after we have completed the installation of the borehole instruments here, there was a magnitude 4.2 earthquake. A magnitude 4.2 earthquake is nothing spectacular. It doesn't produce any big hazard or risk or so. But since we're now in the position to record magnitudes down to 0, we can detect many small events that may occur before or after such a magnitude 4 earthquake. And this was actually the case for this earthquake. So what you see here is the waveform, basically the ground motion of the main shock. So this is the magnitude 4.2 earthquake. And then you have aftershocks here, smaller earthquakes afterwards. But in this case, the remarkable phenomenon was that we also had earthquakes before the magnitude 4.2 earthquake. And this is actually a new study that I'm also going to present later on this meeting as a regular science talk. So we have observed many small earthquakes before the big one, which in this case was a magnitude 4 earthquake. And if we apply sophisticated processing techniques and stuff, and if we would process these in real time, we would be able to come up, in this case, with a measurement which is, in this case, the average of cross-correlation, and I don't want to bother you with details. But the main point here is that with this kind of data that we're recording now, we are able to detect a certain proxy that shows a maximum in characteristics of small-scale earthquakes before a bigger one occurs. And that is something that has been discussed or is discussed for decades, but has not been observed in the field until like 10 years ago or so. There are a few examples like the Japan earthquake 2011, like the last big earthquake in South America, also the Istanbul earthquake in 1999, and now finally this small one here, where we see a certain characteristic in seismicity pattern that occurs before a large earthquake, which might, if we further develop this technique in the future, to apply improved forecasting techniques, and then at some point maybe even real-time forecasting in order to reduce the impacts of pending large earthquakes. So with this, I would like to summarize my talk and conclude. Large earthquakes along tectonic plate boundaries pose a substantial hazard and risk to ever-growing population centers. Modern seismic monitoring is important for state-of-the-art hazard assessments in order to reduce the risk as good as possible. Intense research efforts are currently carried out to monitor the North Anatolian fault zone below the Sea of Marmara. These include near-fault surface and downhole arrays to detect small-scale seismicity in order to understand the physical processes now in the light of the pending big one. And microseismic data from the recently installed plate boundary observatory offshore Istanbul indicate that the Princess Island segment offshore is currently locked and needs to be considered as a potential nucleation point for a magnitude 7 event, just 15 to 20 kilometers away from Istanbul. And with this, I would like to close my talk, and I'll be happy to answer your questions.